Anyone? Okay, everyone seems pretty set. So we will start off with our first panel of the day. Awesome. So our biology panel will be a 2.5-hour long 5-speaker panel, as most of our other subjects go. And we'll be diving into the application of math and medicine, the importance of microbes in brain development, the use of bioinformatics in understanding microbial populations and complex human diseases, and the science behind memory forgetting. Before we get started, I would like to remind everyone of a few etiquette rules for all of our panels. So please refrain from disrupting the speaker while they're talking, of course. Make sure that you're muted at all times when they're talking. Please wait to ask any questions verbally until the Q&A session at the end of the speaker presentation. And please don't write anything discriminatory or offensive in the chat. If you do, and we see that you're consistently denying these stipulations, we will remove you from the Zoom session, in which case you probably won't be able to join again. So make sure that you're very conscientious of what you're saying. And so without further ado, Akshaya Annapragada is our very first biology speaker, and we're super excited for her to join us today. Akshaya is currently an MD PhD student at Johns Hopkins University, and she just earned her Master's of Science and BA in Applied Mathematics and Bioengineering at Harvard University. Today, she's going to be discussing the application of mathematics and engineering to solve problems in health and medicine. So everyone, please welcome Akshaya as she dives into the intersection of math and medicine throughout her college journey.
Hi, everyone. I'm really happy to be here today. I'll go ahead and share my screen so you can see some slides I prepared. So does that look okay to everyone? Perfect.
Yep.
So yeah, thank you so much for the lovely introduction, Diana. As Diana said, today I'll be talking with you about my work at the intersection of math and medicine. So just as a little bit about myself, while I was at Harvard, I was a research assistant at the School of Engineering and Applied Sciences and at the School of Public Health. And I was also the managing editor of the Harvard Political Review and did some advocacy work as part of our Women in Computer Science group. And now I'm a first-year MD PhD student at the Johns Hopkins University School of Medicine. And I'll be sharing some examples from my research first, and then trying to have a conversation with you about this. And I'm happy to take questions at the end. So to get started, one of the things that I'm really interested in is how mathematical models and machine learning can be used to answer big questions. And when I say big questions, I'm talking about sort of systemic macro level questions, things that affect global health, policy, and clinical systems. And I think when looking at these kinds of questions, taking a mathematical approach has several advantages. First, it allows you to use and learn from real-world data. So in practice, data is noisy. It's often messy, and different types of data are collected in different ways and at different intervals. And computational approaches are really good at finding ways to make sense from all this noise. Modeling also lets you try different scenarios quickly and efficiently, in circumstances where a controlled experiment may be impossible. And it also lets you capture those really complex dynamics in order to design and evaluate tailored interventions. So these are some of the reasons that I think mathematical modeling has so much potential in medical applications. Now, another thing that I'm interested in is model interpretation, which is the idea that once we have a model or an algorithm, we need to understand what it does and how and why it makes the decision that it does. So these memes that I have here, they're kind of jokes, but I think they're also representative of this broader idea that machine learning and mathematical models more generally are black boxes, and that we can't possibly know what happens inside of them. So we have data and we give it to the model, and then the model tells us what to do, and we do it blindly. But this is actually really dangerous. It allows us to create models that reflect human errors and biases, and it prevents us from gaining new knowledge about what kinds of factors matter in a system. So something that I look at a lot in my research is interpreting models after they're built and trying to use this to gain insights into medical practice. So with those general principles in mind, I'd like to share 3 examples from my own research where I've built, evaluated, and interpreted mathematical models with the goal of answering some kind of medical or clinical question. So for my first example, I'd like to talk with you about work I did with the Golden Lab at Harvard to mathematically model poultry vaccination programs and design interventions designed to enable sustainable food sources in Madagascar. So the summer after my first year of college, I spent time in Madagascar working with the Golden Lab. And we were interested in sustainable food sources for really remote communities in Madagascar that are reliant on hunting wild meats in the rainforest, things like bats and lemurs. In these communities, there are already staggeringly high rates of malnutrition. As many as 50% of children under 5 are nutritionally stunted. And as the rainforest declines, it's only exacerbating this food insecurity. Moreover, consuming wild meats poses a risk for the transmission of zoonotic diseases. Now, chickens are a potential domesticated alternative to wild meats. However, they are highly susceptible to Newcastle disease, which is a fatal respiratory disease endemic to Madagascar that kills large proportions of flocks. So this makes chicken an unreliable food source. People don't want to invest money and resources in raising chickens if they're just going to die before they can be eaten or sold. Now, vaccinating chickens against Newcastle disease is possible, but mounting a vaccination campaign is really hard in the context of some of the most remote locations on Earth, without electricity and reliable cold chains. Therefore, we turned to data on chicken populations to try to model possible interventions. So in my work, I used data that field teams from our lab had been collecting on Malagasy chicken dynamics for several years. So things like births and deaths and purchases and sales and consumption, which are all ways that chickens enter and exit the population. And we also use knowledge of the vaccine, for example, that it must be administered 3 times a year to maintain immunity. And then I used all these different data to build a system of differential equations to model chicken populations in Madagascar under various vaccination regimes. And I solved this system numerically. And then I interpreted the solutions with respect to 2 different quantification metrics. So the first was population doubling, which is a measure of population growth. In Madagascar, human populations are increasing rapidly, and food security pressures are increasing as well. Therefore, to meet this demand, it's important that vaccinations suppress chicken deaths enough that flock sizes can grow. And we found that this type of population doubling was readily possible, with 40% vaccination coverage over 5 or more years. But the second factor we looked at was herd immunity, which is the idea that once a certain proportion of a population is immune, then disease outbreaks won't really spread. So we know from other studies that this metric is around 85% for Newcastle disease. But it turns out that triennial vaccination can't achieve this. Because of the time scale in which chickens are born and die, it just might not be possible to use vaccination to maintain this pool of immune population over long time periods. So this modeling gave us important insights into how vaccination could be used to stabilize chickens as a sustainable food source. Now, one thing that I think is really cool is that this vaccination program is currently being used in several Malagasy communities. So that's an example of how modeling insights can be translated into actual interventions. So now I'll switch tracks completely because I want to give sort of a different vignette about my research. And I want to talk about work I did at Baylor College of Medicine and Texas Children's Hospital to detect child abuse in the electronic medical record. So non-accidental trauma, or NAT, is a clinical euphemism for child abuse. And it turns out that child abuse can be difficult to detect and diagnose for several reasons. First of all, the patients are usually young and nonverbal, and given the situation, you may not be able to rely on their caretakers to be accurate conveyors of information. The clinical presentations are also just confusing. So to give you an example, this could be a fairly typical clinical picture. You have an infant with a skull fracture, cerebral hemorrhage, and localized bruising. The mother reports that the infant was on the bed, she turned her back, then heard a crash, and found the baby on the floor crying. This immediately begs the question, is the injury mechanism described consistent with the injuries the child presents with? If not, this might be physical abuse, and now there are questions surrounding who was responsible, whether the story that the adults are telling is consistent, and whether CPS should be involved. Now, if the injury mechanism is consistent with the injuries, you still have questions over whether this was truly an accident, or whether the parents failed to monitor the child adequately, which could be neglect. So regardless of the determination, there are still questions surrounding whether this is a pattern of injuries, whether they're complicating social circumstances, and how serious the injury is. So this seems really complicated. But now add in that smaller community hospitals rarely have physicians specifically trained in child protection, and that children may see several different healthcare providers across numerous clinical sites and time points. And you have a pretty difficult problem. But these challenges are compounded by the fact that much of the information needed to come to a decision is in the electronic medical record, which is largely free text notes. So it's hard to automate its processing. And the stakes are incredibly high. Unlike in many medical applications, both false positives and false negatives are really bad. So to give an example, in some medical applications, false positives aren't great, but they can be investigated by further testing. However, with NAT, false positives can lead to traumatic separations from caring families. So it's really important to get it right quickly, effectively, and the very first time that there's a suspicion of NAT. Therefore, we ask the question, how can we find ways to process the massive amounts of text in the medical record to flag possible cases of abuse for physician follow-up? So here we use natural language processing to numerically encode the free text in the medical record, and then we pass these encodings to neural networks that were able to predict the probability that a specific patient record corresponded to abuse. So we tried 3 different natural language processing techniques. In Bag of Words, we take all the words in the record, scramble them up, and assign values to them. So there could be tens of thousands of words in the record, and we consider all of them. In contrast, for rules-based, we consulted with expert physicians to identify phrases in the medical record that could be important, and then we scored each record for the presence or absence of these phrases. Finally, in word embeddings, we used a pre-trained structured text representation to encode the medical records, kind of like using a translation from another language to make sense of this specific record. Finally, when we passed these encodings to the neural networks, we had mixed success in making predictions. Ultimately, the encoding strategy that was most successful was Bag of Words. And when used with a neural network, it had accuracy and AUC of over 90%. So just as a quick aside, AUC is a measure of the trade-offs between false positives and false negatives, and higher values indicate stronger performance. So this was really great results. We had a model that made good predictions. However, we didn't know a lot about how the model was making predictions, which is concerning, because for something like child abuse detection that is known to have racial and socioeconomic biases, it's important that our models aren't learning those biases. So we used something called a saliency analysis to look at the most important model inputs. And we found that they were highly relevant radiological words, things like fracture, swelling, or head, as well as the phrase history of domestic violence. Now, all of these are documented in the scientific literature to be signs of abuse or correlated with abuse. And importantly, they aren't racial or socioeconomic factors that reflect an underlying bias in diagnosis. So this is a really important point, I think. By using model interpretation, after construction, we were able to gain insights into what parts of the medical record were important to the detection of child abuse, and make sure that what we were paying attention to made sense. So now, for the final example I'll give today, I want to talk about my recent senior thesis work with the Golden Lab and Professor Milind Tambe at Harvard, where I developed models to predict malaria and anemia in remote areas of Madagascar. So just to set some background, these are some pictures of the communities in Madagascar where I was working. Unfortunately, these are some of the poorest communities on Earth with really severe health challenges. There's very high malnutrition, with about 50% of children under 5 being growth stunted. And these nutritional deficiencies contribute to staggeringly high rates of anemia, while malaria prevalence is also very high and concentrated in these remote communities. These high disease burdens exist against a background of low access to healthcare, with over 50% of the population living more than 5 kilometers from a health center. Unfortunately, that last factor makes diagnosing malaria and anemia really difficult, since both of these diseases require blood samples to diagnose. So for folks far from clinics with the needed staff and equipment, they can be almost impossible to diagnose. An additional complication is that in areas where these diseases are prevalent, the coincidence of the two is common. This coincidence is especially lethal. By itself, anemia causes a decrease in red blood cells, and untreated malaria leads red blood cells to burst and die. So the combination of the two diseases can cause a precipitous drop in red blood cells. That has a fatality rate of about 50%. Therefore, it's really important to find ways to diagnose malaria and anemia using non-clinical variables so that we can figure out who needs treatment at a hospital urgently and who's at risk for these diseases. So in my thesis, I used a data set of over 5,000 individuals from 24 sites across Madagascar that came from 4 different regions with really different environments. The people were both male and female and of all ages, and I also had over 1,000 different non-clinical variables. So things relating to diet and nutrition, economic status, demographics, income, etc. And what I did was use these variables that can be easily assessed outside of a clinic to build predictive models of disease status. So I built 3 types of models. The first used a technique called principal component analysis that transforms the data into an alternative space and then tries to look at which variables are responsible for variance in disease status. This didn't work very well because, unsurprisingly, a lot of variables contributed to this variance rather than just a small set. The second type of model was logistic regression, which tries to fit a logistic function to the data and then approximate the relationship. And this was overall pretty accurate, but it missed a lot of individuals with disease. So it was good at predicting negative individuals, but not good at predicting positive individuals, which is a problem for a medical application. The third type of model I tried was neural networks, which are a type of deep learning model that are really good at capturing nonlinear relationships. And these models were really good. They were 80 to 90% accurate and identified positive patients effectively. So this is the kind of model you could try to deploy in the field. Next, I tried to use statistical tools to reverse the models and figure out which variables were important to disease status classification, with the idea that these variables could become targets for public health interventions. And what I found is that outside of a few obvious biological factors surrounding age and sex, the majority of important variables had to do with poverty. Limited access to food, nutrients, safe water, and sanitation, as well as gender inequality, seemed to be big drivers of disease. In contrast, wealth and things that go with it were protective factors. And I think this is an interesting conclusion, because it tells us that I took the most sophisticated mathematical models in the world and threw them at this problem. And what they came back with was essentially that poverty alleviation and development work may be the most useful thing we can do to prevent malaria and anemia. So I see these results as a call for broad, multi-sector development programs that can help lift communities out of poverty, consequently reducing disease burden. But the other thing that I think is cool is that I came to this conclusion by building mathematical models and then turning them on their head and interpreting them. So I think this type of interpretation is a powerful technique for understanding complex phenomenon that seem opaque at first. So now that's an overview of my research. And now I'll try to offer some brief advice for others interested in this field. So to be honest, I feel a little silly trying to offer advice here. I'm not nearly as accomplished as many of the other speakers this weekend who are like distinguished professors and experts in their field. So it's a real honor to be speaking alongside them. But the event organizers did ask that I include this section. So I'm gonna do my best to offer sort of a student's perspective. So I first want to talk a little bit about getting involved in research as a young student, particularly in high school or even early in college, when you have a lot of interest and enthusiasm, but may not have a ton of technical mathematical skills. So first of all, getting data can be a big challenge. You probably saw from the examples I gave, almost all of the data I used to build models was data members of the labs I worked in collected in the field, or it was data from the hospital I worked. And these types of data tend to be confidential. So I think that can sometimes be a barrier to working in this field unless you're part of a big academic enterprise that has the data you need. But good news, not all data is like this. And I think relying on publicly available data sets can be great for learning and exploration. One of the sources I used in the past is Kaggle, which is a website that has a ton of interesting data sets freely available. So there's currently several on COVID-19, and there are cancer imaging data sets and all kinds of other interesting things. Another big piece of advice I have is to learn to code. You can start doing this today, and it's one of those skills that takes time to build and requires practice. But if you can code effectively and efficiently, it makes it that much easier for you to get involved in projects when you find them. So I'd recommend Python, which has a ton of free open source libraries and frameworks to support almost anything in the data science and mathematical modeling realm. I'd also recommend looking for ways to enter science fairs and competitions. So when I was in high school, I entered both the Science and Engineering Fair of Houston and the Siemens competitions, and I had a lot of fun. even if you don't discover anything earth-shaking, and I certainly didn't. They do give you experience in planning and executing a research project. Finally, I look into summer research programs at universities that allow high school students to work in university labs as assistants during the summer. These can be a great way to learn and start getting experience. Now, as far as more personal advice, I think one thing that served me well is saying yes to anything that comes along. So you probably saw that I've worked on a lot of different topics and in very different settings, from the field in Madagascar to an academic hospital. And I think that these have all been valuable opportunities, and they've all sort of built on each other and helped me develop a portfolio of work. The way I see it, you never know what you'll like until you try it, and connections tend to sort of snowball. So the more involved and enthusiastic you are, the more chances you get. And you never know which one of those will be the one you fall in love with. So on this note, I'd also stress the importance of seeking out good mentors and positive teams. In all the projects I talked about, I've been really fortunate to learn from incredible professors and to work alongside colleagues who I've had a lot of fun doing science with. And I think this is key. Mentors and colleagues can help you get projects done, for sure, but they can also help you plan out your career and be successful, and they can really make or break your research experience. So I think it's important to be intentional in finding supportive, knowledgeable mentors and lab communities. And I also think it's pretty important to collaborate across disciplines and try to draw on the strengths and tools of different fields. Whether you're looking at engineering or math or medicine, I think bringing them together can be really valuable. And the other big piece of advice I have is to always keep doors open. The best way I know to do this is to just, as a principal, do your best work on every project you're on. I think it's unrealistic to assume that you'll enjoy everything you work on, but the way I see it, doing good work is sort of a muscle, and you have to exercise it to make it stronger. So no matter what, if you do the best you can at anything you're working on now, learn as much as you can and try to go above and beyond wherever you can. This sets you up to be able to do exactly what you want in the future. And then I also think it's important to make plans and set goals and just constantly be evaluating and reprioritizing. So I like to set, short-term goals for myself as well as medium and longer-term goals that concern my academic plans, my career choices, and where I want to be in the next week or the next year or even the next decade. So I think these are some strategies that work for me, and I hope some of them are helpful for you too. And then finally, I would be remiss if I didn't thank and acknowledge the tremendous number of people who've contributed to this research alongside me and served as mentors and colleagues in doing this work. I'd like to offer special acknowledgement to my main mentors on these projects, Professor Chris Golden at the Harvard School of Public Health, Professor Zbigniew Starosolski at Baylor College of Medicine, and Professor Milind Thambe at the Harvard School of Engineering and Applied Sciences. I've also listed the key publications and abstracts that I've authored on these projects in case anyone's interested in reading more. And now I would be happy to answer any questions.
Awesome. Thank you so much, Akshaya. Let's see what everyone has to ask. All right, while we're waiting for anyone to come up with questions, I have a few of my own. So these are less related to like your exact work, but more about your professional pathway. What was your favorite aspect of attending Harvard as an undergrad?
Yeah, absolutely. I think this is probably true of any college, but I just enjoyed living and learning with peers who are interested in a lot of things that I was interested in too. And I think I had really great opportunities just to work on exactly what I wanted to work on and the way I wanted to work on with the people that I was excited to be with. And I think that sort of communal aspect is a really favorable thing that a lot of people enjoy about college, and I did too.
For sure. Let's see. YouTube, anybody?
Yeah, so I can kind of answer these two questions together about the 90% success rate and the question about implementing ML algorithms. So yeah, a 90% accuracy rate does mean that 10% of these are incorrect. And I think that is like a problem. But one thing that I do like to think about is that this is not one of those things that we're great at doing without computers. So physicians making these diagnoses are only right about 75, 80% of the time on their first guess. There's usually quite extensive follow-up. So if on our first pass we can get to 90%, that's a good opportunity to then involve physicians in further workup of the patient. So I see this more as like an early detection flag than the final, end of story, we are deciding what's happening. And then the question about getting child abuse detectors implemented in hospitals. So no, this is not yet implemented in hospitals. And in general, I think there are a lot of interesting regulatory questions around how machine learning algorithms will be used in a hospital environment, because right now there's a lot of great research happening on them. But as you probably know, there are a lot of laws concerning what you can do in a hospital. There's privacy laws, there's the FDA that regulates products that are being used in medical settings. And it's a pretty big question how these can be used. And I think right now, a lot of people are finding out that translating research to clinical practice can be a tough thing. And so we're continuing to work on this and try to improve it and hopefully get it used in the hospital. But I think that the main steps there really are doing the research, getting it published, and extensively validating it before you really try to make it a commercial product. Okay, there's a question about if I can recommend sources, books, advice on improving science skills. So beyond the sort of general advice to look for data sets to start learning to code, I'm not sure I have specific books or sources, but I would say that there are a lot of freely available resources on the internet. I think Code Academy comes to mind if you want to start learning Python. And then I think my general advice would be to just start playing around with it as quickly as you can. So you can spend a lot of time reading textbooks. And I think that reading textbooks can be really valuable. But where I really found specific books to be useful is once I know what the specific challenge I have is, and then I go to look up what can I do with it. I don't know that for myself, reading books cover to cover before starting has been extremely useful. But that's just kind of my thought. When is a good time to start joining research teams in high school? And where did I learn to create all the different types of models? Okay, so joining research teams, I would say now. If there's a research team that you're interested in and you want to join it, join it. If you hate it, you can always find a way to stop doing it after. You don't want to leave people in the lurch, but it's always fine to quit things that you don't enjoy. But if you do enjoy it, why not start your future career today? So that's kind of my advice on that. And then creating different types of models, I think some from coursework, but a lot of it is also reading the literature. So once I know this is the medical problem I want to go after, I start reading scientific papers and trying to see what's already been done and then building from there. And then maybe I go read some mathematical and computer science papers to figure out how to implement the model. So I think it's pretty iterative. I definitely didn't learn all of this from my coursework before I started doing research. Okay. What sort of research can we do without needing to go to labs in public places? Research that we can do online from the safety of our home with the guidance of a mentor online. Yeah, so I think that this kind of computational research is actually a great example of COVID-proof research. You don't have to go outside, you can sit inside with your laptop. And I think finding those publicly available data sets and just diving in is a great place to start. And as far as mentors online, I think anyone who would have been a mentor in person pre-COVID can be a mentor online. You just need to chat with them, and everything doesn't translate perfectly to Zoom, but I think a lot of things can be done over video chat or phone calls that you might have once done in person. Okay, how much do college professors assist you in finding research opportunities like yours? Yeah, so I think that varies quite a bit. I definitely don't think that there are college professors who are just, taking out ads in the newspaper saying, I need a student to come write the following code and then it will be done and the research project will be published. But I do think that most professors have some idea of what they want students in their group to work on. They're usually not going to say oh, just come on in, I'll give you money and time and resources, do whatever you want. So I would say the balance is usually the professor will come up with the big idea, but you'll come up with the implementation steps. They probably won't tell you what model to use. They'll just tell you, we need to find a model that answers questions in this realm. And then you'll hone in on the question and you'll hone in on the techniques. Okay, what is the difference between Python and R for data analysis? Which one is better? So as far as differences, I think the big thing is that R is a statistical language, and there are toolkits that are being built to do more modeling approaches, but fundamentally R was originally used for data science statistics type things, whereas Python is just a multi-purpose scripting language. And again, now there are libraries being built specifically for modeling and machine learning and things like that. But I think they both just started out with very different purposes, though you can now do kind of the same thing as neither one. And in my opinion, I mean, I guess I would say Python, but a lot of that is I learned Python first and I know how to use Python. Whereas when I see R code, I have to think how to use it. So it just kind of, I prefer Python, but I think it's open to your preference. And then I do use MATLAB a little bit. I think MATLAB really shines in signal processing and in some like image interpretation tasks, whereas Python is a little lighter weight and just easier to use when I'm trying to do some exploratory data analysis.
It is actually 9 a.m., so maybe we can have one last question if anyone has any lingering thoughts. Oh.
Okay, I'll try to answer those last two together. So prerequisites, it really depends. You just need to talk to the professor or look into the opportunity. But in general, I think even if you don't have all the prereqs, if you have some of them and you're enthusiastic about getting the other ones, I don't think it's going to be a huge barrier. And then advice I would give to someone considering the MD PhD path and recommend to become a competitive student. Okay, the only advice I really have if you're considering it is to go for it. Like, I mean, I don't know, I'm only a year into it, but it seems pretty okay so far. And I think that it's really cool to be thinking that one day I'm going to be both treating patients and finding ways to, come up with better science to help those same patients better. So it's, I think it's a good career. And what I recommend students to do to become a competitive student. Yeah, so I think those two pieces of advice that I had about just saying yes to opportunities that come your way and doing the best you can at everything you touch are kind of the two I have. Like, it takes practice to be good at things. So practice being good at things. And then that way, when the thing you really, really want to make your career out of comes along, you'll kind of know what it takes to be great at it. So that's kind of my advice. But I wish you all best of luck in your own paths to becoming students and researchers.
All right, thank you so much, Akshaya. I hope everyone really enjoyed learning about Akshaya's application of math in medicine and how she was using mathematical modeling to design vaccine interventions and, help preventively diagnose child abuse.